Hello and good morning. Welcome to another live stream of Chemistry 222. How's everybody doing out there today? I'm going to start off by posting a few useful links to some resources that we have here in the Learning Center. Enjoying the sunshine. That is good. It's a nice sunny day today. I wish I could be outside playing instead of inside doing stuff, but that's half the fun of life. So here's a link to the PSU's Learning Center website. I like to post these at the beginning of each live stream. There's also a link to their Facebook account and their Instagram. You can follow them on there to get updates of new resources that they have available. We're always trying to innovate and have new ideas for things and whatnot. So stay in touch and whatnot. And today we are going to talk about the strengths of acids and bases, going into Ka and Kb values, as well as percent ionizations. We're going to talk about like salt solutions and how they dissociate into acids and bases as well. And polyprotic acids is the other topic we're going to try to get into. So let's get started. Switch over to my iPad here. So when we talk about acid and base strengths, acid/base. Strong acids, and there's probably about 6 different strong acids that you should really pay attention to and make note of. I have now they're listed right above my head. Those strong acids and bases they fully dissociate in water. So anytime you add, for example, perchloric acid or hydrochloric acid to water, it breaks up completely into basically hydrogen ions and chloride ions for the case of hydrochloric acid. The hydrogen ions are going to create hydronium for all of those, and the chloride ions are really just going to be floating around in the water, very happy to just be floating around in their ionic form. Strong acids basically have a very, very, very weak conjugate base, which means the conjugate base is incredibly happy being negatively charged or just being in that basic form. So we can say strong acids, I say essentially fully dissociate and they have very weak conjugate base. Therefore, to make a weak conjugate base, that means the conjugate base is incredibly stable. The idea of a weak acid, this is an acid that when put into water, it creates this equilibrium state. So not all of the acid's going to disassociate in the water. It's going to create a conjugate base, and that conjugate base is a little bit stronger of a base. It's not a really strong base. It's not like our strong bases up top here. Those strong bases are usually an ionic compound of sorts, where like lithium hydroxide or something like that, where the lithium is really just a counterbalance for that OH base. Similar with sodium hydroxide or potassium hydroxide. They're all just counter ions in that case. But either way, the weak acids are going to be in equilibrium with their conjugate base. So they're going to be constantly transferring back and forth, but we get to this equilibrium state where the rate of changing from acid to base is equal to the rate of changing from base to acid. And that's that equilibrium state y'all have been talking about. So I can say that weak acids are in equilibrium. And the strength of weak acids and bases can be measured by their Ka or Kb value. And their Ka and Kb value is basically that equilibrium constant at equilibrium, which is, I'm going to write it as Ka is equal to the concentration of H3O plus times A minus. A minus being basically that conjugate base that's there after it's lost the H, the proton. And then I can say HA being the acid. So it's whatever the A is, could be relative, but on the bottom here it's its acidic form because it has that hydrogen ion, and then on the top the the A minus is where it's lost it, that conjugate base. Similarly, Kb is going to be equal to OH minus HA over A minus. We talked a little bit about last week about Kw. Do we remember what Kw is? Anybody? Perfect. That's right. Kw is basically 10 to the negative 14. Or 1 times 10 to the negative 14. It's the same. And the Kw is equal to Ka times Kb. We could write it out as H3O plus times A minus divided by HA, times, put a big dot, OH minus times HA divided by A minus. Seems really complicated, but you can see that these A's are going to cancel out because we're doing multiplication. We have one on the top and one on the bottom. Same with these HA's. And this is just going to leave us with H3O plus times OH minus, which is the definition of Kw. And this is a useful relationship because we could find Ka if we know Kb, because Ka is going to equal Kw divided by Kb, and similarly Kb is going to equal Kw divided by Ka. It's a really cool relationship. If you have one, you can always kind of work your way around and find the other. It's similar to this pH box we talked about last week. Here we were talking about the concentrations of hydroxide and hydronium and how we can swap back and forth between those with Kw. You can do the same idea with Ka and Kb using these relationships here. So if you have Ka, just take Kw divided by Ka, you'll get Kb, and vice versa for Kb. So if you have one, you can find the other, which makes it really easy and convenient. And we're going to utilize that a little bit today. One more topic. Any questions on that? Kind of what I've gone over, the idea of strong acids, strong bases, weak acids, weak bases, and the relationship of Ka, Kw, and Kb. If not, I'm going to move on. We're going to talk about, I'm just going to mention here this idea of percent ionization, which is really just how much of your acid has disassociated and created hydrogen ions for you. And we can measure this based off of the concentration of hydronium, or we can get that from the pH, right? So we could say that this is equal to the concentration of H3O plus, so it's how much of it has disassociated divided by, I'm going to say HA naught. And that little zero at the bottom kind of means the initial concentration of your acid. So for every acid that loses a hydrogen ion, it creates that conjugate base. So what we're looking for really is how that ratio of conjugate base to the initial acid. but the conjugate base should be equal to the concentration of hydronium. So that's why we can write it like this. And we're going to multiply it by 100 because it's a percent. And we can use that if we're ever looking about if they ever ask what is the percent ionization, it's really just the simple formula here. And we can say, and we should note that the concentration of H3O plus is going to be equal to the concentration of the conjugate base. We'll say A minus, assuming you have monoprotic acid. So let's try a few problems using some of these. Let's go here. So this is asking what is the pH of a 0.0516 molar solution of nitrous acid, which is HNO2, and they're saying, the pH is 2.34, and they want to know what its Ka value is. So I'm going to write that reaction out. This is HNO2, and it's an aqueous, which means it's just floating in water, dissociating. We have H2O, which is a liquid. It's going to be in equilibrium with H3O plus, which is aqueous. That's an AQ plus NO2 minus. Whenever you're writing out these balanced equilibrium equations, it's really just start with whatever acid you have, add water to it, right? And then the water is going to gain a hydrogen ion if it's an acid that you have to begin with, and the acid loses it to become its conjugate base. But it's a good thing to kind of write out, and you can visualize what it is. Now, when they give us this concentration here of nitrous acid, that's really kind of the formal concentration. That's before it's disassociated, before any reaction happens. So we call that the initial concentration. So I'm going to write up here in initial. We can then utilize the idea that we know its initial concentration, and we know what the pH is, so we can determine from that pH what the concentration of hydronium is, because we know we know that the pH of it is going to be this once it's at equilibrium. So to find the pH, which equation should we be using in this case? The ice table, we definitely want to use the ice table to find the Ka value at the end of this. But first we need to find that concentration of hydronium. I guess we don't need to do that first. Okay, let's set up that ice table. Because if you wanted to, if we know the pH is equal to 2.34, this is what I was getting at, we can say that the concentration of H3O plus is going to equal the 10 to the power of negative 2.34. That's just converting pH into that concentration of hydronium, kind of going up the left side of my box above me here. And if we plug that into our calculator, 10 to the power of negative 2.34, we get 0.0457. 0.0457. And that's going to be our concentration of H3. So now we can set up our ice table. I'm going to write out the reaction again. HNO2 plus H2O. It's going to be in equilibrium with H3O plus NO2 minus. So what is our initial concentration? Can I spell? I can't spell. I'm just going to say initial. Of HNO2. What is given to us up here in the problem? So I can say that's 0.0516. These are all in molarity. Water we don't care about. This whole column, since it's a liquid, it's our solvent. We're not going to have that as part of the ice table. What is the change in, or what is the initial concentration of hydronium before any of that reaction happened? Zero, yeah. And it's really kind of approximately zero. Any water always has a little bit of hydronium in it. If it's neutral water, it's going to be 10 to the, it would really be 10 to the negative 7. But since this value is especially so much smaller than this, when we start adding things together, it gets lost in the sig figs. So for simplicities, we just call it 0. And NO2 minus, what is the concentration of that initially? Also 0, because the reaction hasn't happened yet, right? So the change in this reaction, how much of these are going to actually change? What's the change in concentration of our nitrous acid? Minus X, that's good. If we didn't know the pH, that would definitely be true, because we wouldn't know how much of it's changing. In this case, since we know the pH, all of this extra hydrogen that showed up in our solution at equilibrium came from this guy, our acid. So we know that our change needs to be equal to that change in that concentration of hydrogen. So I can say my change is 0.0457. And my change in hydronium would then go up by that same amount, 0.0457. Our conjugate base here, NO2 minus, what's the concentration of that? What's the change in that concentration? Any ideas? Exactly. It would be the same because our conjugate base came from our acid. So our acid splits up into a hydrogen and a conjugate base, and that hydrogen ion bonds to water, creates hydronium. So our concentration of hydronium and our concentration of our conjugate base in this case is exactly the same. And our acid, the concentration of our acid is decreased by that same amount. That's why if you didn't know the pH, you'd put a negative X here. You put a negative X here, an X here, and an X there. Because our acid is, the concentration of our acid is decreasing while the concentration of hydronium and our conjugate base is increasing by that same amount. So then at equilibrium, we can just add these values up. So if we took 0.0516, our initial, and we subtract from that our change, we should find our equilibrium value in this case. 0.0516 minus 0.0457 is, did I type that in right? I did. Oh, there's an extra zero. I put an extra zero. I forgot an extra zero there. So I should have an extra zero in everything. Let's fix that. It's an easy thing to do, at least for me, to drop a zero in things. That should have an extra zero in it. I didn't read my calculator right. So then all of these need that same extra zero. So, like I said here, this is really 10 to the negative 7. 10 to the negative 7 plus this value, once you look at the significant figures, is still this value. That's why we say it's essentially 0. And one more 0 to insert. It's a nice thing about working on a tablet, you can make space. All right, let's go back to this equation. Insert an extra 0 in there. There we are. 0.04703. And then these two, since they just went up, they would just be this value. And we want to find ultimately the Ka. Yeah, exactly. When the pH is given, we don't need to use X because X is for that change in concentration. So if you know what that change in concentration is, because you know the pH of it, or the concentration of hydronium in this case, then you can use that value for all of them across the board. We'll do another one next where you actually have to use X and use the quadratic equation and all that other fun stuff. So now to find our Ka value, we had that formula, a couple pages back. This guy, the concentration of hydronium times the conjugate base concentration divided by the concentration of the acid. So really, it's always products divided by reactants. So looking at these, the products here is going to be the concentration of hydronium, 0.00457, times the concentration of the conjugate base. Since that's the same, I'm just going to throw a squared up there. And we're going to divide by the concentration of the acid. So dividing by 0.04703, we should be able to find our Ka value. And really, yeah, what is the Ka? So we can, where's my calculator? 0.004, I already have it. Let's use, where'd it go? This one. So I can take my value, just paste it in there. I'm going to square it. Divide it by this value here. I like to use the values that are stored in my calculator from previous calculations to make sure I'm not rounding intermittently, if I can say the word. There we go. So that's our concentration of hydronium times our concentration of the conjugate base. That's why it's squared at the top, divided by our concentration of the acid. Gives us 4.44 times 10 to the negative 4. And making sure I do my sig figs properly. We have 3 initial ones here. Yeah, this should be good. So that was 4.44 times 10 to the negative 4. So if we wanted to find the Kb value for the same reaction, what would that be? Do we have to do a whole nother ice table for the base reaction, kind of going backwards? We could do that. It would just take a long time. There's a quick or easy way to do that. Kw divided by Ka. Perfect. Kw divided by Ka. So that's just taking 10 to the negative 14th. And we're going to divide it by our 4.4 times 10 to the negative 4th. Put parentheses around there. 10 to the power negative 14 divided by my previous answer. Something's wrong there. I think I need to insert a parenthesis. Maybe not. Yep, that should be it, I think. 2.25 times 10 to the negative 11. Yeah, that sounds right. There should be a point in there. And that's how we get our conjugate base. So let's try the next one. It's another ice table in this one. We're going to actually have to use a quadratic equation, which makes it fun. We're going to find the concentration of hydroxide ion, the pOH, and the pH of a 0.25 molar solution. So we need to find 3 things here. The concentration of hydroxide. Which one is hydroxide? What's the chemical formula for it? Yep, OH minus. And the pOH and the pH of a 0.25 molar solution. Trimethylamine, which is a weak base. You know what? One second here. So we can do this. I think that's the same way. I grabbed the wrong problem that I wanted to. Because that one, I don't think we need to. They're giving us the pH again. All right. No, they're not. Okay. I'm just not spacing. So now we have to draw our ice table. So trimethylamine is an amine. Let's look up trimethylamine. It's an amine with 3 methyl groups on it, I believe. Right? Yeah. So that would be an N with 3 CH3s bonded to it. Okay, and that's going to be basic because it's got an extra lone pair floating there. So this would be, let's say, CH3 3N plus H2O liquid is going to be in equilibrium with, in this case it's basic, so it's going to gain that hydrogen. So that'd be CH3 3NH plus OH minus. So that's our balanced chemical reaction. That's how it's going on there. Now, when we make our ice table, the initial concentration is going to be what for our base? Yeah, 0.25 molar. How about for our water? What's our initial concentration there? None. We don't care about water. Exactly. And then our initial concentration for the other two is going to be 0 and 0, because that reaction really hasn't happened yet. And this is still approximately 0 because it's really 10 to the negative 7, and we don't care about it because it's too small compared to our molarity. If we had a really small concentration of our base initially, it would then it would start to matter. So if we had a concentration of our base of 10 to the negative 7 or so, now we're right on par with that, so it actually start to matter. But since this is so much bigger than 10 to the negative 7, it doesn't matter. The change. What is the change in this case? We don't know the pH here just yet. We don't know the pOH. We don't know the concentrations of anything. So we have to leave it as a negative X. So we know the concentration of that base is going to go down as the acid and the hydroxide increase. So in this case, this will be a positive X and a positive X here. So at equilibrium, we can write out this expression, 0.25 minus X is the concentration. And then these concentrations are there and there. Just making a little bit of room. So now writing out our KB equation. KB would be equal to, again, it's the concentration of the products divided by the reactants. So in this case, the products are just X and X. So it'll be X squared, X times X, divide by 0.25 minus X. And now we have this state where it's going to be we can't just solve for X really easily. We have to break it down into a quadratic equation. So we can do that simply by breaking this all. For the quadratic equation, we need it in an ax squared plus bx plus c equals 0 format. So we got to make this equation go to this form. To do that, I'm going to multiply each side by the denominator of this fraction, which would leave me with KB times 0.25x is equal to x squared. So when I multiply the right side here by this, it just cancels out my denominator. I'm left with x squared. Multiply the left side, I just get this. Distribute this in. I'm going to move it over. So first let's move it over. So I can say 0 is equal to x squared minus KB times 0.25 minus x. And then distribute that negative KB in. So that's 0 is equal to x squared minus KB times, or say 0.25 KB plus x. Make sure you get that plus x because it's the negative times that negative. So now we have our quadratic equation in this form. We can plug it into the quadratic equation, which is negative b plus or minus the square root b squared minus 4ac divided by 2a, where a, b, and c are the coefficients of the different terms there. So plugging those in, this becomes negative 0.25 plus or minus the square root of negative 0.25 squared minus 4 times a is just 1, so we're going to leave that out, times c. C in this case is just going to be x. No. Oh, C is, I'm sorry, I'm doing this wrong. Well, I forgot. This value here is really over here. A little rearrangement. Or KB is really what we're looking for there. Concentration of let me make sure we're on the right page. Yeah, concentration of Kb is equal to that times that times that. And it didn't give us, I feel like we want to jump over and look up our value for Kb to find that x. Let's try looking up dimethylamine. There we are. That's dimethylamine. I was looking at the Kb table to see if we have a value for Kb so I can find those concentrations. Here I can switch over to that. There we can see. This is just on the appendix H of your book. This is dimethylamine. There's no trimethylamine. Oh wait. Oh, that's the one I just did. Ah, there it is. In the book, they give us the Kb value. I didn't write that down. So the Kb value is equal to 6.3 times 10 to the negative 5. And that makes our life easier. So now we can plug these in to this value, where this is C, 1 is going to be B, and 1 is going to be A. So that's negative 1 plus or minus the square root of 1 squared minus 4 times 1 times this 0.25 times 6.3 times 10 to the negative 5. Which really, 4 times 0.25 is really just going to equal 1. There. So we're really just subtracting off this 6.3 times 10 to the negative 5 under there. And we divide it all by 2. So plugging these in, I'm going to do what's under that square root first. 1 squared minus 6.3 e to the negative 5 So I mean that's really close to 1. We have -1, then plus that divided by 2. So say plus this. I forgot my parentheses. Equals this guy. So if we're adding 1 to that, doesn't quite do it. It's always going to be a negative value. I thought it should be a positive value. Oh, they're just assuming that. Try it again with negative. I think that's just going to be more negative. So in the book, they're actually just assuming that x is much less than 0.25, which makes this a lot easier. Because of this Kb value being 10 to the -5, being a lot less than that molarity. I didn't see that Kb value to begin with. Not the page. Oh, thank you. Sorry about that. There you are. So in the book, they were saying that because this Kb value is so much smaller than our initial concentration, we can just assume that x is a lot smaller than this. So when we get to this point, we can solve much simpler. So I'm going to copy this. I'll just erase. So instead of doing the quadratic formula for this, they're saying we can assume that 0.25 minus x is essentially 0.25. And then solving for, just ignoring that negative x. Because if we were to put in a really small value here, it would, again, significant figures is going to cut it off, and it's not going to affect the value. So then that means that 0.25 times Kb, which we have a value for now, Kb is equal to 6.3 times 10 to the -5, is going to equal x squared. And we can just take the square root of both sides. So then in my calculator, I can take the square root of 0.25 times 6.3 e to the -5, I said. Yeah. And that's just going to equal 0.004. Yeah. So that's going to be for the concentration of the base and the concentration of our conjugate acid in that case. And we want to solve for the concentration of OH, which we found now. This is equal to the concentration of OH minus. We also need to find the POH and the pH. So how can we find the POH of this guy? Oh, so you don't always want to ignore the x, only if your Kb value is really small. If you have a really weak base, essentially, you could ignore that x. If your Kb value is along like 10 to the -2 or something to that effect, anything where when you plug in this equation, you calculate the significant figures and your value changes, then you don't want to ignore that x. Anytime they're within, say, an order of magnitude of 10 to the 2 or 10 to the -2, I'd say don't ignore it. Anything that's bigger than that, especially like 10 to the 5, 10 to the 6, then it's probably fine to ignore. Because it all comes down to that significant figures. If you actually plug it in, nothing changes, then nothing's going to change, right? So here we have the concentration of the hydroxide. We just need to find the pOH. We know that the pOH, you got it, is going to be equal to, well, so 10 to the power for pOH is not quite right. But negative log of the hydronium is for pH, right? For pOH, it's really negative log of the concentration of OH. So anytime you have that P of something, P of X or P of OH, pH, we're taking the concentration of whatever that something is. In this case, OH. And we're taking the negative log of that to find that pOH. If we had the pOH value and we wanted to get back to that concentration, that's when we would take 10 to the power of the negative pOH to get back to our concentration. So doing this, negative log of our concentration gives us 2.40. And how can we find from that the pH now that we have the pOH? There you go. You got it. 14 minus 2.4 is 11.59. Don't want to do that. So then pH is equal to 11.59. Any questions on that process? I drew a blank here not knowing my KB value, so always read the problem fully, otherwise you might run into a snag like I did. We got about 10 more minutes left. I want to run through real quick the idea of hydrolysis of salts. This works very similar to what we've already talked about. It's just we're dealing with salts now, and salts usually have, it does get kind of confusing from time to time when you're dealing with these. A lot of it is come down to your ice table. If you have a KB value or a Ka value, try to relate that to your molarity, see if you can simplify things. Otherwise, your quadratic formula is going to tell you basically that concentration of one of them when you get down to it. A lot of it comes down to remembering this pH box and how to convert between pH, pOH, and the concentrations thereof. And again, you can do something very similar with a KB box, Ka box. Let me switch here. So like, just doing a quick search of a Ka box and chemistry, because that is food, images. So yeah, here's one that's, this is really the same idea as your KB box, where you have the Ka in the top left corner and then the pKa. So you can go back and forth between those the same way you would with, say, your concentration of hydrogen and your pH. Similarly, you can go down from Ka to Kb by dividing Kw by Ka or Kb, so you can go back and forth and some. Yeah, print that out and print out that pOH box, the pH box. Both of those are really useful, so you can transfer between those. Keep them in your notes somewhere. So just doing a search on the internet, this is how I found this for KB box, Ka or pKa box for chemistry. So a lot of fun resources up there for stuff like that. Just if you don't put chemistry in, you get food, which looks delicious. It's about lunchtime anyways. But I digress. So salts. Real quickly, salts are ionic compounds composed of cations and anions. So you hear about this a lot. Your basic table salt is basically sodium chloride. And sodium is it's an ionic compound, and chloride is going to be just kind of a negatively charged. So sodium is in one of your group 1 metals there, so it's +1 charged all the time. And these basically just float in there. It's called a counterbalanced ion to the chloride ion, because chloride, you can't just have chloride negatively charged sitting there. It has to be balanced with something else to stabilize it. So you can put it in a jar, sit it on the shelf. That's how we get salt. But salts can be any of those, any 2 different types of ions kind of bonded together. And a lot of these will completely dissociate in water. So another example of that is hydronium. Ammonium, NH4, bonded to chloride. Ammonium chloride, which is a solid. And if you put it in water, it'll completely dissociate into NH4 plus. And chloride minus. In this case, NH4 plus is an acid compound. It's acidic, right? It's got an extra hydrogen there. It's positively charged. It's going to want to get rid of that hydrogen. The chloride, on the other hand, this can act as a base, but it's an incredibly weak base. In fact, the conjugate acid of this base is HCl. HCl is one of our strong acids up there, right? Hydrochloric acid, which means it's going to completely dissociate in water. So the Ka of this is going to be approximately infinity, where the Kb is going to be about 0. Because once it's fully dissociated, we're doing the products divided by the reactants for the Kb and Ka values. In the Ka example, the product the reactant HCl is going to be almost completely gone, so almost 0. So we end up with this Ka value of near infinity. So in this case, chloride doesn't really act as an acid or a base, but ammonium does. It'll act as an acid. So we can then write NH4 plus H2O. This is a liquid form. It's going to produce NH3 ammonia. Well, this is ammonium plus H3O plus. And then we can write a Ka value for this, where Ka is going to be equal to the concentration of NH3 times the concentration of H3O plus divided by NH4 plus. And that's kind of how it would dissociate and why the chloride doesn't really work, because this Ka value, it's the conjugate acid is a strong acid in that case. So we don't really have to worry about that. But for this salt, basically, depending on what those ions are, anytime you put any solid salt into water and it dissolves, you want to look at what it dissolves into, what those ions are going to be, and then figure out what's the Ka, Kb values for those ions. And if they're part of that strong base or strong acid, you can essentially ignore that Ka, Kb, because it's not going to change the acidity very much. But then based off of this reaction, we could then determine what the acidity of that reaction is going to be. I'm about out of time. I don't have time to go into a problem for that. But are there any questions that I can answer or help you with? Not at the moment. All right, no problem. I do have tutoring hours just after this from 1 o'clock all the way till 5 o'clock. So you can always, if you have any questions or you run into any questions, feel free to drop into my tutoring hours or make an appointment. There should be a link in the Pinji site right above me to make an appointment with one of our wonderful tutors here. Have a great day, and then get out and enjoy some of the sunshine, eh? No problem. It's my pleasure.